Hey guys, so today we're going to be doing our lesson on thermodynamics. There are some calculations in this lesson as well, though one of the calculations we're going to be doing is about efficiency, which is actually something that you should have done in grade 9, so we'll just kind of be reviewing that. Okay, so this lesson focuses on the laws of thermodynamics. We're going to be going over the different types of thermodynamic systems. We're going to be looking at the first and second laws of thermodynamics. We're going to be looking at what efficiency and entropy mean, and then doing some calculations for both thermodynamics and efficiency. And then we're going to briefly be looking at the efficiency of different energy sources. So thermodynamics is the study of the relationship between work, energy, and heat. And the laws of thermodynamics just describe the transfer of thermal energy, which is heat, during different energy conversions. So for example, when you're converting work into energy or one type of energy into another, thermodynamics describes the transfers of heat that take place during those. There are 3 different types of systems in thermodynamics. In open systems, both matter and energy can move in and out. So the Earth is an example of an open system. Matter can come in, like meteorites, or matter can leave, like when we shoot someone off to the moon. Energy can also come in the form of like solar radiation or stuff like that from the sun, and then heat can also dissipate away from Earth back out into space, which is a form of energy. Closed systems are where energy can move in and out, but matter cannot. So this is what we usually kind of get when we're like doing experiments here on Earth in like a laboratory or something like that. You're trying to stop matter from being lost and gained when you're doing like a chemical reaction or something, but you are still going to be having like heat energy and stuff like that escape your reaction. And then an isolated system is where neither energy or matter can move in and out. This is incredibly difficult to actually achieve because you need essentially a vacuum in order to be working in. But it is what we pretend all of our systems are for the sake of like our calculations and stuff like that when we were in the earlier portion of this physics unit. So the first law of thermodynamics says energy cannot be created or destroyed, can just be transformed from one form to another or transferred from one object to another. So we talked about this quite a bit in some of our previous lessons, like with a pendulum and stuff like that, that you have energy being converted from gravitational potential to kinetic, back to gravitational potential, and none of that energy should ever be lost or gained. That pendulum would just keep swinging back and forth and back and forth. We do know that some of that energy is lost from the pendulum, but it's not just destroyed entirely. That energy doesn't just disappear, it is transferred to the surrounding air molecules through air resistance and stuff like that. Energy will not be lost or gained in an isolated system. It will always remain constant, which is what we assume when we're doing our mechanical kinetic energy calculations or our gravitational potential energy calculations. Of course, we don't live in an isolated system. Energy is lost or gained from the thing we're studying, but it's never lost or gained entirely. It might just be lost to the surrounding atmosphere or something like that, or to another object if friction is involved. This formula is used to calculate the amount of energy in a system, which again, shouldn't change if it's an isolated system, but most systems aren't isolated. E is the energy of the system, Q is the heat gained or lost in the system, and W is the work done either to or by the system. Q will be positive if heat is gained, Q will be negative if heat is lost. So while you will be given this formula on your formula sheet, you do have to like memorize these 2 points here about Q and W. So yeah, if temperature goes up, Q is positive. If temperature goes down, Q is negative. If work is being done on the system, your W value will be positive. If work is being done by the system on its surroundings, work will be negative. So I picture this like if I were the system. If I had to like do work, like clean my room, I don't like cleaning my room, so that would be negative for me. So W is negative if me, the system, has to do work. However, if I am getting work done on me, like if I'm getting a massage or something like that, I love a good massage, so that would be positive. So work being done on me, on the system, is positive. And because we're dealing with energy here, our units are all going to be in joules. So let's try some practice calculations. Okay, so for our first calculation, it says a system starts out with 210 joules of heat. It then performs 87 joules of work on its surrounding as the heat decreased to 80 joules. What is the final energy of the system? So E equals Q plus W. First, we have to figure out what our Q is, which is the amount of heat lost or gained. So in order to do that, we just take the final amount of heat minus the initial amount of heat. That'll be our Q value. And then our work, it says the system performs 87 joules of work. So obviously our W value is going to be 87, but because the system is the one performing the work on its surroundings, that is a negative 87. Then we just do 80 minus 210, which is negative 130. The good thing we have a negative here because it does say the heat is being decreased. So we should have had a negative. And then subtract 87 is negative 217 joules, would be our final answer. For the second one, it says a system has 400 joules of energy, while 120 joules of work is being done on it. How much heat is lost or gained? So try this question on your own, pause for a second, and then come back and see the answer. Okay, so for this problem, we're starting off with the same formula, but this time we plug in the 400 joules for the amount of energy the system has, also plug in the 120 for the work, and since the work is being done on the system, it is a positive 120, and then we're going to solve for Q. So in order to do this, we need to move our 120 to the other side, so a positive 120, we will subtract it to cancel it out. What we do to one side, we must also do to the other. That gives us 280 equals Q. So that would be our answer. It's also joules. So thermodynamics will affect all systems, including ones that occur in nature. So in food chains, energy is always passed from one trophic level to another. So as it's like moving from like producers to herbivores to carnivores and stuff like that. Whenever one organism eats another, the energy from the prey or the plant is passed on to the predator or the herbivore. And anytime this happens, energy in the food, which is chemical energy, is going to be converted into useful energy that the body of the animal can actually use to do work. However, about 90% of the energy in food is actually lost to the surroundings as heat or other forms of useless energy. So only about 10% of the energy that's in things that you eat can actually be like efficiently used by your body. So it's a very inefficient process. And that brings us to the second law of thermodynamics, which there's actually 3 parts of. The first just says heat always flows from hotter to cooler areas on its own. So if you were to like touch your hand against something that's cold in the wintertime, that cold object is going to suck the heat out of your hand, and the heat will leave your hand and go into the cold object. That is why your hand would get cold. This happens in water too. If you go swimming in water, chances are the water is colder than your body temperature, so you will lose heat from your body into the surrounding water. Every isolated system also becomes disordered over time. So unless you put work into keeping things organized, they will naturally become more disorganized over time. And then the last one is that it's not possible to completely convert heat into useful work. Essentially, what this means is that no process can ever be 100% efficient. There will always be some energy that is in the form of thermal energy, and that's not useful energy as far as work being done is concerned. So entropy has to do with that second part of the second law of thermodynamics, the law or the part of the law that says every isolated system becomes disordered over time. Entropy is the amount of disorder in a system, and it will always increase naturally if a system is just left to its own devices. In order to maintain order or decrease entropy, you have to use energy. So that's what this little guy chucking bricks at the bottom is demonstrating. If you just have bricks and start throwing them, chances are they're going to end up in this big jumbled mess because they're just naturally going to become very disordered. It's very unlikely if you're just throwing bricks that they're going to stack into a nice wall like this. You are, in order to get them to be nice and organized like this, going to have to put some energy into it or some work into it. Okay, useful energy and wasted energy. So all machines and our bodies are designed to convert one form of energy into another form in order to complete a specific task. The energy that performs the task is called useful energy, but during any process, some energy will always be converted into a useless form, which is considered the wasted energy. And heat is usually that useless form of energy that is just lost to the surroundings. When we're talking about efficiency, we're talking about how well can a system convert one form of energy into a useful form of energy. So essentially, the less wasted energy or useless energy that's produced, the more efficient a system is. The more heat that is lost during an energy transformation, the less efficient a system is. So for example, if we have electrical energy going into a light bulb, the useful energy would be the light that's actually produced, which is a type of electromagnetic energy. So you hope to get as much electrical energy converted into electromagnetic energy as possible. However, some of that electrical energy is going to get converted into heat during that process, which is why especially older light bulbs tend to heat up a lot. More efficient light bulbs are better at staying cool because they don't waste as much energy in the form of heat. So this is the formula for efficiency. The percent efficiency is the useful energy divided by the total amount of energy that was input. And then we just multiply by 100 at the end in order to convert it into a percentage. So the useful energy is just the amount of energy that got put in minus whatever was wasted. Whatever was left over is used. So let's try some practice questions with this. Okay, so this first question here says the gasoline in my car used during ignition contains 990 joules of energy. It takes 160 joules of energy to start the car. What is the percent efficiency? So I have my percent efficiency formula. The EU, also EUO, is the amount of energy that is actually used to start the car. So that is the 160 joules. We're going to divide that by the input, which is the amount of energy that actually goes into the car for ignition, which is the 990 joules. So we just divide those, 160 divided by 990 gives us 0.16 repeating. And of course, we times it by 100 to convert it into a percent. So 16.16 repeating percent. So try the next two on your own. Just pause here for a moment and then come back for the answers. Okay, so for this next problem, we're starting with the same formula, but this time we're given the percent efficiency, and then we're also told how much energy the engine uses, and we're asked for the energy input. So I'm going to plug in my percentage, also plug in my used energy. Now there's two different ways to move on from here. We can either right away get rid of this times by 100 by dividing by 100. And of course, we must then divide the other side by 100, which brings us to 0.26 equals 300 over EI. Alternatively, you could have just right away ignored the times 100 and plugged in your percentage as a decimal. Essentially, it's the same thing. You're just not actually showing that step because, as you may know, we can never, ever do calculations with percentages. We always have to turn them into decimals. So you could just plug it in as a decimal right away, and that means you don't have to do anything with this 100. Or if you actually plug it in as a percent, you just divide by 100 right away, and then it turns it into a decimal. Anyway. Now we have 0.26 equals 300 divided by EI. And of course, our rule is that when we have a fraction like this, the thing on the bottom must be the thing that moves. So we are going to multiply by EI on both sides. That gives us EI times 0.26 equals 300. And now in order to get our energy input by itself, we will divide the 0.26 away from it. What we do to one side, we must also do to the other. That leaves us with EI equals 300 divided by 0.26 is 1153.85 joules. So that is how much energy was input into the engine, and then only 300 joules of it was actually used, which was 26% efficient. Okay, so for this last question here, once again, we're going to start with the same formula. It says I put 35 joules of electrical energy into a light bulb that runs at 80% efficiency. How much energy is lost? So I don't know how much energy was used. I do know that the amount put into the light bulb, which is the input, was 35 joules. And my percent efficiency was 80%, which I'm just going to plug in as 0.8, which means I can ignore the times 100. Again, you could also put that in as 80% and then just divide by the 100. And then, as always, whatever is on the bottom of this fraction here has to be the thing that moves to the other side. So times 35 times 35. 0.8 times 35 is 28, is my EU. Now, that is not my final answer, though. This is my useful energy. It asked how much energy was lost or how much was wasted, would be another way of saying that. And so in order to do that, we are going to briefly move on to a second step here. And all we're going to do is say, okay, if the total energy was 35 joules and we used 28 of it, if we just subtract those, whatever's left over must be the amount that was lost. So 35 minus 28 is 7 joules of energy. That is how much of this initial amount of energy we were not able to convert into useful energy and was just lost as heat instead. Okay, so we're going to finish off this lesson by just comparing efficiency in a couple different systems. So when it comes to engines, gas-fueled internal combustion engines, like what you find in most cars, are about 15% efficient. Diesel-powered engines, much more efficient at 40%, and electric engines are actually able to convert over 90% of the input energy into useful energy. Of course, no engine system or any system for that matter here on Earth will ever be 100% efficient. No system that we have here on Earth exists in a vacuum. So you'll never have 100% efficiency. Friction and entropy are the main causes of energy loss, and friction in this case also includes air resistance. So with the case of friction or air resistance, you're having energy both converted into heat, which is why when you like rub two things together, they get warm, and also energy just being passed on to the other object. And then entropy, the fact that disorder happens naturally, which includes the diffusion of heat. You can use lubrication to reduce friction and insulation to reduce heat loss to try and increase efficiency. If we look at some non-renewable energy sources, both coal and oil combustion are about 30 to 35% efficient. Coal does have more energy in it than any type of fossil fuel, so more than like natural gas or oil. And there's more of it, but it also causes more pollution, which is why a lot of places are moving away from coal. Oil is less polluting, so still polluting, than coal, but it is the one that we're likely going to run out of first, the one we have the least amount of here on Earth. Natural gas plants are the most efficient of non-renewable energy sources, at about 44% efficient. It does also have more energy than oil, though less than coal. And then nuclear power is about 33% efficient, but it is better for the environment than fossil fuels, assuming that there's not some sort of, massive catastrophe in all of the nuclear power plants. And then if we look at renewable sources of energy, hydroelectric energy sources are about 90% efficient, so very high efficiency. Wind power is about 26% efficient, geothermal, quite weak at only about 16% efficient. And then depending on the type of solar cell, solar power ranges from 21 to 12% efficient. Why did I put those in backwards order? Let's say 12 to 21% efficient. Okay, that's it for today's lesson.